Welcome to this course on power quality. So, we will discuss now the analysis and design of passive power filter. The design procedure for passive shunt filter generally involve the following steps: estimate or record the input current frequency spectrum of nonlinear load as its displacement power factor, obtain the frequency response of the power distribution equivalent impedance at PCC, where the passive filter is to be connected in the system, and select the number, types and tune frequency of passive filters out of tune single, double, triple, etc., and damp first order or second order or C type filter. Normally, C type filter is recommended for low frequency and high pass or high frequency, and appropriately assign the reactive power to be generated by each unit of passive filter. Estimate the parameter of each unit of passive filter. Evaluate the attenuation factor of each unit of passive filter as a function of the frequency. Check the existence of resonance frequencies of each unit of passive filter, and if these resonance frequencies of passive filter units are close to the current harmonics generated by nonlinear load, then the tune frequency of filter must be changed, and accordingly calculate the new parameters of passive filter to avoid the parallel resonance with supply system. Validate the performance of distribution system with filter scheme connected through simulation, and estimate the harmonic distortion of voltage and current and displacement power factor. This design procedure of passive filter has to be iterated till the satisfactory performance is achieved of the distribution system in terms of total harmonic distortion of the current and voltage and power factor. Like coming to the design of this, in design of this passive shunt filter, in single phase, the third and fifth harmonic filters are designed using a series tuned filter, and high pass filter is designed using a second order damp filter, and in three phase, the fifth and seventh harmonic filters are designed using a series tuned filter, and high pass filter is designed using a second order damp filter. Initially, the size of capacitors is calculated from reactive power requirement of the load. The absolute value of capacitance is calculated as Cn equal to Qc upon m omega Vs square. The trap, the nth harmonics current, the inductance for nth order harmonics is calculated as Ln equal to V upon n square omega square and Cn, where n is the order of harmonics, and the series resistance of the inductor for nth order filter is calculated as Rn equal to n omega Ln upon Qn from this quality formula relation, and this quality factor certainly should be order of we already discussed in between 10 to 100, but absolute value may be around 10 to 30, where the quality factors is the Qn is the quality factor of the inductor for nth harmonic filter, which is normally considered in between 10 to 100. Like the quality factor for high pass filter inductor is considered in between 0.5 to 5 or so. So, that is the method how we really design like on. So, coming to the modeling, simulation and performance of passive power filter. Well, this is the one case study we are taking. This is what I was talking about, voltage fed load. So, you have a diode rectifier followed by a capacitive filter, and in parallel we have a load which may be like a inverter fed induction motor drive, or it can be like a some kind of other load, I mean, which is fed from constant DC voltage. I mean, but adjustable speed AC drive consisting here either induction motor, or you might have a permanent brushless DC motor, or I mean any other motor which are fed from constant voltage, I mean is the total system, but input part we are only considering, but that is the only interface to the grid. So, this if there is no passive filter, it sucks the all harder, you can call it sucks unlimited harmonics depending upon the time constant of capacitor along with the load. So, to block, and in case of three phase, the lowest harmonics which is dominant is the fifth one, the second dominant is seventh one, and then you have a typically 11th and all higher order harmonics. So, that is the reason we are keeping here fifth harmonic block filter, seventh harmonic block filter, and then we are putting 11th and high order block filter. So, this offers a very high impedance these lower order harmonics, I mean, and it blocks all these lower order harmonics, and certainly you can see it here we have a how many like a 2 plus 2 4 and 3 7, and total element 7 into 3 is your 21 element like so this is typically like we consider with the design of it and then the simulation of this. So, this is the typical design data for that load of 50 kilowatt 25 kilowatt with the supply frequency of this, and these are the series filter design data. I mean the fifth tuned filter is 770 microfarad, okay, and then the fifth its inductance is 5.8 millihenry, seventh harmonic 60 microfarad and 3.4 millihenry, and then your high pass is 3 ohm resistance, 48 microfarad and 1.8 inductance. So, this is virtually a well design of the passive filter of this order which is shown there, and well you can see after putting this passive filter with 25 kV load, this is supply voltage which is distortion has reduced, and this is you can see the current supply current which are now close to typically very close to the sinusoidal, and this is the typically you can call it the voltage now at the input of your diode rectifier, which otherwise should be this voltage, but now this is the this voltage. I will explain why this is this voltage, and this is typically the same as load current because it is a series filter, and this is the voltage across the filter. I mean this is the voltage, you can call it the difference of this and this will appear across the filter because it is coming in series. So, the drop this voltage is the drop between this voltage and this voltage, this will be sine wave, and this is the voltage when you are forcing. Now, earlier only 2 diodes were conducting at a time, because you can understand out of 3 diodes 2 are conducting, and sometime even none of the diodes are conducting, because out of 120 the only 2 diodes should conduct at a time, and but because of discontinuous current you will find even none of the diode is containing capacitor feeding the load, depends on the value of capacitor and the load, let us say the equivalent resistance or so or time constant of it. But now you are forcing to conduct all the diodes, I mean then only these currents are becoming sinusoidal. So, all 3 let us say phases are conducting and you are forcing. So, when you are having a forcing of all 6 devices are conducting, it is like a 3-phase inverter. What kind of, I mean like this capacitor voltage now is reflected here. Are you able to follow? So, it is something like a, you can think about it is a 180 degree mode of operation of like your 3-phase inverter. So, same kind of voltage are appearing here as you can see here like here. Well, this will be helping you later on in design, that is why I am explaining in detail. So, this is the voltage you will be having, seeing it is a kind of like a quasi square wave, but of course, because of the impedance of the circuit this is not also ideal, and current is also not exactly ideal, and the difference of this and this is appearing across passive series filter like I mean also. And you can understand now the voltage, supply voltage TAD is now reduced to 0.05, I mean like quite low, and the TAD of supply current is only 4.89%, which is less than 5% permitted by the standard, even for like. So, you are with this proper passive filter design, we are able to meet the requirement typically of power quality for voltage as well as current. But if we do not keep like a passive filter, this TAD of this voltage will be also substantially high because of the source impedance, and this large harmonic currents will be flowing into the network like. And this is the, you can think about the voltage at the point of common coupling, which I was mentioning here, okay, because it is similar to like a coming 25.29. I mean ideally, I mean in case of 3-phase inverter 180 degree mode of operation it should be around 30%, but you can understand because of this they are not sharp edges, so it is around 25%. So, you can correlate, I mean this covers reasonably like a concept of power electronics in all these circuit, because it is a power electronic circuit and covers that is the TAD out of this like I mean also at the load voltage, but this is not going to affect in any way to the load, because load is still getting, now capacitor is charging more effectively by all the 3 phases. Earlier it was charging hardly by even as only let us say 2 phase, current was flowing from one phase and returning another phase, sometime even the current was not flowing at all. So, now you will find the even the ripple on the capacitor voltage will be also less in that case, that is the benefit of, I mean like you can think about. Now, that was the corresponding to voltage fed load. Why we took an example of voltage fed load earlier, because that is the load nowadays very much used, like all the adjustable speed drive using a diode rectifier followed by capacitive filter, and after that you are using 3-phase voltage source inverter, in general the IGBT based inverter. That is another example which are going to have a modeling and simulation of passive shunt filter for compensation of 6-pulse thyristor converter, and this kind of, I mean converter you can think about with the constant current on this side, with the reasonable fire angle maybe like a 30 degree or even less than 30 degree. You will find this in the typically like a DC motor drive, I mean thyristor converter with fire angle control with DC motor drive, or you might have a like a magnet power supply, or you might have a field excited synchronous motor, I mean like, or typically large alternator field excitation, or even the converter used typically in to derive a current source for the current source inverter. I mean that is also used here, and similar converters are used, of course not this simple configuration, similar converter are used in 12 pulse converter in case of in HVDC also, for which we design the filter. But this is of course 3 phase converter which are also used in number of applications. We are taking a rating of 25 kilowatt load and corresponding to like a typically 30° firing angle, it draws 25 kilo load, and this 6 pulse converter certainly from supply will have drawing the 5th harmonics current. That is the reason we are putting 5th, lowest will be 5th and then 7th, and we can't afford the cost of so many element I told you. Then we design this for 11th order of harmonic, that is the 3rd dominant harmonic, and take care of all higher order harmonics. So, in this case also why we are not having so much element, even we are keeping like a 3 element for each phase, there will be like 11 here, 2 plus 2 4, and then 3 7, 7 into 3 means 21 element, even for these 3 filters like 2 tune filter and 1 high pass filter or so for this thyristor converter. Now, coming to the design this passive filter, I mean we design corresponding to 5th harmonics with this capacitance. I mean you will see capacitance is same. So, what we consider the reactive power reactive power for all the branches of passive filter, I mean you will have a like a 3 into 3 means 9 branches. So, we have divided the reactive power which is required by the thyristor converter at 30° firing angle. We divided that reactive power into 9 parts because there are 9 passive shunt branches and all 9 have a capacitor, and that is the reason capacitor values for all the same we have taken. So, you have to take certainly some design aspect, and then the inductor for 5th harmonic comes 4.4, approximately half comes for 7th, and then for 11th it comes typically order of this. So, that is, and with the quality factor we get the resistance for 5th order, which is the quality factor of this inductor, this is the quality factor of this inductor. I mean like resistance comes from that quality factor, and here the quality factor normally keep we have already mentioned that you have to keep 0.5 to 5, and order around 2 we take quality factor from which we have calculated the resistance. So, this is typically the design coming, we will discuss design also later, and but this is just like a modeling and simulation. So, you can see like this is the supply voltage, this is supply current, you can say close to sinusoidal, and this is the load voltage which are not affected, same voltage, and this is the load current which are not affected by filter, because filter is connected in shunt. So, this is not supposed to disturb the load, okay, and this is the, you can call it going the filter current. So, filter current is nothing but the difference of this current which is the load current and the supply current. So, it has a reactive part because this needs the reactive power, it has to feed reactive power, so that the power factor on displacement factor is also improved closer to unity, and then the harmonics also reduced. So, that is the reason, I mean this when we design for this 25 kVA thyristor converter load this passive filter, and you get the current very close to sinusoidal line. And you can clearly see now typically the here the TID of your voltage come 3.47 only, and the TID of current of course order of 8.55%, but in such a higher rating even the TID permitted little high depends on source impedance like also. Well, where the current TID, load current TID 27.81% or so. So, coming to another example like a 12 pulse, I mean modeling and simulation of performance of passive shunt filter for 12 pulse converter. This is the typical converter you can think about like HVDC or very large rating drive, synchronous motor drive which I was mentioning example, or magnet power supply. So, plenty of harmonic you will find, and we have designed corresponding to 115 kilowatt with the 100 ampere current on this side. Okay, and both converters are connected in series, which is normally similar to like HVDC. So, that you have equal current in both. I mean equal current certainly will help that balancing automatically of both the converter current, and then the voltage rating is increased because both voltages are connected in series. And the isolation is of course providing the right voltage, because in HVDC you go to high voltage. So, this we have from generation side to go to high voltage transmission system, also that is for HVDC, but for other application also, I mean such kind of things. So, this is 11th harmonic, 12th you can call it 12 pulse converter, but less than 11th will not be there, all will be cancelled out. So, lowest will be 11, then 13, and next band of 12 and plus minus will be there. So, next will be 23, 25th. So, this is design corresponding to 23rd harmonics, and all higher harmonics are taken care here in this 12 pulse converter. So, this is the design again, I mean from the reactive power of 30° we are calculating the capacitance, all 9 elements there also, and from which we are getting same capacitance for this. And now tune for 11th harmonics you will find the inductor, 13th harmonics we find the inductor, and then 23rd high pass design for 23rd. So, that we get the inductor, and this resistance are calculated from quality factor, typically here for, because that is the inductor resistance like. So, there is a limitation that what value of quality factor you can get in by manufacturing. So, that is the resistance value of those inductors, and this is the resistance normally little higher in the sense because this resistance is kept separately with the quality factor between 0.5 to 5, and we keep order of 2. So, by putting this filter, passive shunt filter for 12 pulse converter, and you can see these are the typical currents like. So, you have a supply voltage, supply current, and you have a load voltage which is really quite good sine wave, and this is the load current, 12 pulse current you can clearly see. Okay. So, it has a reactive power because firing like 30 degree, it has a harmonics, and that is the reason passive, you have a passive shunt filter current. So, it has a reactive power, you are looking that fundamental current is also there, that is reactive power in it, okay, and that is the reason this have a unity power factor on the supply side in spite drawing the reactive power. So, reactive power is provided locally by passive filter as well as you are having by typically harmonics also met locally, it does not go to the supply system like also. So, that is typically you can say the TAD of this supply current comes 5.34 and the voltage TAD reduces to 2.91 only. So, it meets up to some extent the standard for large power rating, which is permitted up to 8% depends on the source impedance like also, and this is the typically load current. For 12 pulse converter the TAD comes order of 15.21% for this current like. So, this is load current, but you can certainly see in that the load is not affected by this kind of phenomena like. Now, coming to the limitations of passive shunt filter, the limitations are the passive filters are not adaptable for varying system conditions and remain rigid once they are installed in an application. The size and tune frequency cannot be altered easily. The change in operating conditions of the system may result in detuning of the filter and it may cause an increased distortion. The design of the passive filter is reasonably affected by source impedance. For a effective filter design, its impedance must be less than source impedance. Another limitation is it may cause in large size of filter in a stiff system with low source impedance, which may result in overcompensation of the reactive power, and this overcompensation may cause over voltage in switching in and under voltage at switching out the passive filter. And these passive filters are designed with large number of elements, and loss damage of some of these elements may change a resonant frequency, and this may result in an increased distortion in the distribution of the permissible limit. In case of large filters, the power losses may substantial and because of resistive elements. Another limitation is the parallel resonance due to the interaction between the source and filter can cause amplification of source, some characteristic and non-characteristic harmony, and size of damped filter becomes large in handling the fundamental and harmonic frequency. The environmental effects such as aging, deterioration, temperature change and detune the filters in random manner, and in some cases even a presence of a small DC component and even a harmonics current may cause saturation of the reactors of the filter, and a special switching is required in switching in and switching out of the passive filter to avoid the switching tangents, because it consists of your you can call it inductor and capacitor which have a switching tangents unlike. So, grounded neutral of a star connected capacitor bank may cause amplification of third harmonics current in some cases, and special protective and monitoring devices are required in passive filter also. Now, coming to a one major limitations of you can call it like of typically of parallel resonance of passive shunt filter, like with supply system, and how we can mitigate it or avoid it in the design, that becomes very interesting problem like. So, what is the resonance with the supply system? So, when a passive shunt filter or even a power factor correction capacitor connected at point of common coupling, it may have a resonance with the supply impedance if some harmonic producing loads are connected at the same point of common coupling. The resonance may happen between the inductive reactance of the supply impedance and capacitive reactance of passive shunt filter of a capacitor used for power factor correction. And as a passive shunt filter is connected in parallel with the supply, a parallel resonance occurs between inductive reactance of supply impedance and capacitive reactance of passive shunt filter. This parallel combination of inductive reactance of the supply system and capacitive reactance of passive filter offers a infinite parallel impedance at a frequency FR when these two reactances become equal, and this frequency FR is known as a parallel resonance frequency. If any frequency of harmonious current producing loads connected at the point of common coupling is at or close to this resonance frequency, a severe voltage distortion and harmonic current amplification may result in this circuit, and this amplification of harmonic current may be many times, and it may be sufficient enough to blow the fuse of or under desired tipping of your passive filter or capacitors. So, this parallel resonance frequency of any system can be determined by using data of the system, which can be explained by an analytical method as follows. The typical example here, you have a supply system, you have a source impedance, you have a transformer, a step down transformer, and then you have a capacitor bank here, maybe for improving the power factor, and then you have a nonlinear load, linear nonlinear load, which we can keep it after equivalent per unit basis or equivalent, like of it, we can have this source impedance, may be referred on typically on the load side, and then we have a like a transformer, short circuit impedance like resistance and reactance, and then we have this capacitor and we have a load, and this can be equated by lumping together equivalent to this, like equivalent impedance. Now, from this impedance network you can calculate the value of feeder resistance on this side, typically ohmic value from kV, your short circuit current level, typically a short circuit MVA, and the from voltage rating, typically that is the angle of this, that is the resistance, and that is typically the reactance of the feeder and reactance, and the data of the feeder in ohms, and LV side it can be transformed to LV low voltage side of the transformer. So, the source impedance can be transferred to low voltage on the turns ratio square, that is the just like a basic concept of transformer impedance transformation from one side to another. The value of the feeder resistance reactance are calculated as in typically from this relation, and these data of the feeder in ohms are referred to LV side, that is typically the relation, and equivalent circuit parameter of transformer referred to the you can call it secondary winding from this relation, that is the per unit, and then multiplied the base impedance for the transformer resistance, winding resistance, short circuit equivalent, and this is the short circuit reactance. So, that is also we are getting on typically on secondary side. So, where RTPU are the per unit reactance resistance parameter of the transformer, and KT is the 3 phase kV rating, and kV is the line voltage of the secondary winding of the transformer, and total equivalent circuit parameter of the system shown in second figure is your RT, that consists of feeder impedance on secondary side and transformer impedance also on secondary side. Similarly, reactance of the low voltage side of the transformer, and the transformer your short circuit reactance, and where the from this reactance you can calculate LT. LT will be XT upon 2 pi f, f is a fundamental frequency of the supply, and from this the equivalent reactance of the capacitor bank can also can be calculated from KVR rating. You have a voltage already of the voltage rating of the capacitor where it is connected. So, you have a XC, and from this you can calculate your typically the capacitance. So, this is inductance of the feeder including the transformer, and this is your capacitance there where capacitor is connected, and then where KVR and KVC are the capacitance of 3 phase KVR rating and line voltage rating and capacitor value in farad of the your passive filter, and the total impedance of the equivalent circuit in shown in that you can call it will be Zi RT plus that omega at particular frequency, it will be plus JT, and then capacitance is connected. After that, if you look into the you have impedance, then the capacitor, and that will be the your total impedance look into of this, you can call it this circuit, and this impedance Zi can be calculated a wide voltage frequency omega to locate the resonance frequency at which the impedance has a maximum value under the parallel resonance. The denominator of impedance must be minimum value. So, it should be minimum value at the frequency of omega r, where the inductive reactance and capacitance must be equal, like. So, from there from this formula of resonance frequency we can calculate omega r this, and omega r will be under root LTC, and this from this we can find out the frequency in hertz also from this relation, and from this relation a resonance frequency may be calculated for the system of data which are given, and if this frequency certainly matches with the some frequency produced or close to the producing load, then you will certainly have amplification because of high impedance and typically of harmonic voltage. So, that is virtually even like you are keeping a passive. So, means that will cause the resonance, and how to avoid this resonance. Then in capacitor of this, I mean this will be lump again. In capacitor we can connect a small inductor in series, and this may avoid the resonance at that particular frequency by putting this inductor and have a resonance frequency of this to another some frequency which is far away from that resonance frequency. And we can find out after this putting this inductor in series with the capacitor, this impedance will be now of capacitor, this filter, I mean capacitor and inductor circuit, and in this now we can find out what will be the now typically the resonance frequency of this of total circuit, and LF is the value of the filter inductance, and from which we can find out now new resonance frequency. From this, in place of LF we have LT plus LF now, and C, and this new resonance frequency will be this, and this new resonance frequency must be very far from the frequency which really can appear in the load. So, the parallel resonance phenomena can be avoided by shifting, or to occur this parallel resonance frequency FR at a value less than the lowest order harmonic current present in the harmonic producing load. So, well, the voltage distortion and harmonic current flowing in the supply system can be computed as follows. So, I mean corresponding to the resonance, the current flowing into the harmonic filter and supply at frequency omega A can be like this is the filter current which will be flowing, okay, typically that is the harmonics producing of the load, and this is the typically into the supply system, where the this is IH is the harmonic current, okay, for any particular harmonic flowing. So, how much will be the going to be this harmonic current into the filter for HH harmonics, and how much will be the going to be in the supply, how much into the filter, that is the these currents, like you can calculate like and the harmonic voltage at each harmonic produced. So, you can find out what will be that point of common coupling the harmonic voltage. So, you have ISH, you can call it the current flowing into the supply multiply the source impedance or supply impedance, total supply impedance at that particular harmonic, I mean that is the total harmonic voltage at the point of common coupling. So, this will not, I mean if it is the resonance, this voltage will also go high, like. So, voltage distortion and harmonic current flowing into the supply system can be computed as follows. So, these equations may be used to calculate the harmonic currents and voltage to find out the duty of harmonic filter and TID of the PCC voltage and supply current. However, the fundamental currents of the supply and filter can be calculated as IS1 total kVA, IS1 fundamental current can be calculated total kVA of the load divided by √3 into nominal line PCC line voltage, and the typically you can call it fundamental current can be calculated nominal voltage, and typically the impedance of the filter, that is the filter fundamental current, how much it is flowing into it, like also. And then the voltage distortion, typically harmonic voltage across the capacitor and inductor may be calculated from how much is the harmonic current going into the filter. So, that will be the harmonic voltage divided by the capacitor, that is the voltage across the capacitor, this is the voltage across the inductor. I mean that we have to all check that this voltage are not going excessive, and I mean the typically resonances are not there. So, as the voltage across the filter capacitor is higher by 5 to 10%, and therefore, these capacitors are selective little higher voltage rating. However, the fundamental reactive power rating had to be derated as. So, now kVA rating typically will be kVR n divided by FA upon n into VA upon Vn square, where A represents actual and represents the nominal or rated quantity like